Introduction. Band pass filters are a type of electronic circuit that use active components such as op-amps to perform filtering function. They allow only signals within a specific frequency range to pass through, effectively filtering out signals of undesired frequencies. They are a combination of high-pass filter and low-pass filter, offering excellent selectivity with sharper roll-off and steeper cut-off slopes compared to passive filter. Application of band-pass filter includes preventing transmitter interference with other stations at adjacent frequencies, allowing only signals of required frequency to pass in a receiver, optimizing signal-to-noise ratio and sensitivity, and usage in sonar, seismology, EEGs, electrocardiograms, lasers, LiDARs, and audio signal processing.
My name is Siti Asya binti Ismail and my matric number is TE210102. Next, we're going to take a look at the manual calculation used in this project. So the purpose of doing this manual calculation is to calculate the important parameters such as the resistor and capacitor values that we're going to use in the implementation of the circuit for this project. So we have been given the specification, which is the mid gain value equal to 70, the low cut-off frequency equal to 3 kHz, and the high cut-off frequency equal to 20 kHz. So since we know that this is the fourth order bandpass active filter, so we're going to use the fourth normalized denomination polynomials n equal to 4, where the value is 1 plus 0.765s plus s squared times 1 plus 1.848s plus s squared. So next, we move to the first part of the manual calculation, which is the high pass filter. So we know that the formula of gain equal to 1 plus RF over RA. So we assume RA1 equal to RA2 equal to 10 kilo ohm. Hence, we get the reference resistor value equal to 12.35 kilo ohm for RF1 and for RF2 equal to 1.52 kilo ohm. So next, we want to determine the value of resistor and capacitor. So we assume the value of R, which is R1, R2, R3 and R4 equal to 24 kilo ohm. And from the assumed value of resistor, we can calculate the value of capacitor. We get the capacitor value C1 equal to C2 equal to C3 equal to C4 equal to 2.2 nanofarad. Okay, next, we move to the second part of the manual calculation, which is the low pass filter. So for the low pass filter, we assume the RB1 and RB2 the same as RA1 and RA2, which is equal to 10 kilo ohm. And from the assumed value, we can find the RF3 and RF4 value, where RF3 equal to 12.35 kilo ohm and the RF4 equal to 1.52 kilo ohm. Okay, since we know the given high cut-off frequency is equal to 20 kilohertz, so we assume the value of R for this low pass filter is equal to 3.6 kilo ohm. So from the assumed value of resistor, we calculate the value of capacitor, which is equal to also 2.2 nanofarad. And then next we move to the last part for this manual calculation, which is the part C, where we know the gain value given is equal to 70. So from that, we calculate the total gain, which is AV equal to 6.629, and then from that we can calculate the RA5, where to calculate RA5 we assume RF equal to 15 kilo ohm, and then we get the RA5 equal to 1.56 kilo ohm. So that's all for manual calculation of this project.
Next, I will present about the simulation circuit, and the software simulation that our group use is Proteus 8 Professional, and this is our 4-order band-pass filter circuit, consists of two 4-order high-pass filter and two 4-order low-pass filter and another one for the extra non-inverting amplifier to fulfill our requirement project value mid-gain equals to 70. And all the value of the R and C is calculated based from the manual calculation presented before, and we will rounding into the real value RC before we construct the circuit. Then we will give the terminal input for the amplifier in the pin 7 and the pin 4 to 15 positive volt and the negative 15 volt. And we can generate out our result at the pin 6 non-inverting amplifier. So this is the simulation result output for our frequency response graph generated from our circuit in the Proteus. Based on the frequency response graph that our group gain, we can know that our mid gain AV equals to 36.8 dB, and from the maximum gain we can find the low cutoff frequency FL or FC1 and the high cutoff frequency FH or FC2, and by minus 3 dB, and we will get our low cutoff frequency equals to 3.08 kilohertz and our high cutoff frequency FH equals to 19.1 kilohertz. And from the frequency response graph, we can analyze that it consists of high pass filter and a low pass filter. And when we compare the result for our simulation with the given value, we can know that it is almost the same.
Okay, so after the experiment testing have been done in the lab, so this is the experimental result that we get from the experiment that we have conducted. So this is the graph that we plot, which is the gain versus frequency. The data that we collect from the experiment, we choose the frequency range starting from 500 Hz to 40 kHz. So from this variation of frequency, we come up with the gain value by using the formula of V out peak to peak divided by V in peak to peak. So with the obtained gain value that we get from the calculation using the formula, so we plotted the graph. So this is the graph that we get based on the data that we collect in the lab. So as we can see from this result, from this graph, the mid gain is equal to 36.1 dB. So after we minus the mid gain with negative 3 dB, we get the new gain value, which is 33.1 dB. So this gain value work as a new reference for us to identify the low cutoff frequency and the high cutoff frequency of this experimental result. So from this experimental result, we get the low cutoff frequency is equal to 3.2 kilohertz and the high cutoff frequency equal to 19.3 kilohertz. Next, we're going to take a look at the comparison result between the specification given, which is the theoretical value, and also the software simulation value, and also the experimental value. So first of all, we can see the mid-gain value of the given value or the theoretical value is 70 in unitless or 36.9 dB. As for the simulation value, we get the mid-gain value equal to 36.8 dB. And as for the experimental value, we get the mid-gain equal to 36.1 dB. Next, let's take a look at the low cutoff frequency. So the theoretical value of or the given value of low cutoff frequency is equal to 3 kHz. But as for the simulation, we get the value of low cutoff frequency equal to 3.08 kilohertz. And as for the experimental value, we get, which is from the graph, we get the low cut-off frequency equal to 3.2 kilohertz. Next, for the high cut-off frequency, the given theoretical value of high cut-off frequency is 20 kilohertz, and the simulation value we get 19.1 kilohertz, and for the experimental value we get 19.3 kilohertz. As for the bandwidth, the given bandwidth or the calculated value of bandwidth we get 17 kilohertz, but as for the simulation value we get the 16.02 kilohertz, and the experimental value is equal to 16.1 kilohertz. And then same goes along the way to the center frequency and quality factor, as can be seen in this table. So what can we conclude from the obtained value from the simulation and experimental? We can see a slight differences or slight deviation in terms of value compared to the theoretical value. So what can we say is that these differences or this deviation may be caused by an internal factor or resistance during simulation and experiment in the lab. So I think that's all for the analysis of the experimental result.
Now, for the conclusion, the project successfully implemented a fourth-order bandpass filter using op-amps adhering to specific design specs. The mid-gain was successfully tuned to the desired level, while the low cutoff and high cutoff frequencies slightly deviated from the specified values. The circuit was validated through simulation using Proteus software before experimentation, providing confidence in design accuracy. Practical challenges that could affect the filter's performance were carefully considered during the experimental phase. The project provided hands-on experience in designing, implementing, and testing a fourth-order bandpass filter, emphasizing the importance of theoretical understanding and simulation validation. It stands as a testament to the synergy between theory and practice in electronic circuit design. Thank you.